Hi, welcome to the Fairbanks Museum Earth Science Lab. I'm Michael, and today we're going to be talking about refraction. We're going to be talking about how light refracts when it passes through objects. This may not be a term that you've ever seen before, refraction, but I'm sure that you're familiar with its kind of sister term, reflection, right? We've talked about light before. In this class, we know that it's a form of radiation energy that has a couple special properties. So light is really, it moves as a wave, as an invisible wave through the environment, right? And you've probably all seen that waves of light have the ability to bounce off of certain objects. You've probably all used a mirror or another reflective surface to reflect light. Now, refraction is another special property of light, and it has to do with when light moves through something, but it changes as it moves through something. So we're able to change light by reflecting it, which we're familiar with, but we're also able to change light by refracting it. Now, the most common substance that we can refract light through is water. You've probably all seen this before, whether in a glass of water that you have in your house or in a pond or something like that. Whenever you see an object in water, it oftentimes looks strange, looks different. As I move this ruler in our glass of water here, you can see how the look of the ruler changes in a really strange way. It looks very wide at the bottom, where there's lots of water in between the camera and the ruler. When the ruler is outside of the water, of course, it doesn't change like that. So what's going on here? We are seeing refraction happening inside of this jug of water here. To explain refraction, we have to talk a little bit about the part of light that we have a hard time understanding, and that's how fast light moves. Light is the fastest thing in the whole universe. In a vacuum, which means in a space with no air or nothing to slow down the light, light can move at 186,000 miles per second. That means that if you could run at the speed of light, you could run laps around the Earth, many laps, in just 1 second. That's how fast light is. Now, out in outer space, it's almost a vacuum out there. And so light moves at almost 186,000 miles per second. But here on Earth, light is moving through the air, through our atmosphere. And even though it doesn't seem like it would to us, that air, the particles, the molecules, all of the different gases in the air actually slow down that light. So the light that's moving around you in the room that you're in right now isn't going at 186,000 miles per second. It's going a little bit slower. And when light moves, the best way to say this is that when light passes from one material into another material, it makes the light slow down, and it actually changes the angle that that wave of light is moving, right? So, this is hard to think about, but the light that's moving through the air right now between the camera and the glass is moving extremely fast. We know that. But when it passes through the glass and then through the water, that wave of light has to slow down. Light moves slower in water than it does in the air. Slower is a relative term here. That light is still moving at thousands of miles per second, still extremely fast, but just a little bit slower than it was moving in the air. And as a result, when that light hits this glass and then all of a sudden slows down, the light beam that's shooting into the glass, it's actually going to hit the glass and then change its angle as it moves through the glass. that might be very hard to understand because we can't see light waves and they're moving so fast. But the result that we can see is the way objects look when they're in a refractive substance like water. The strange look of this ruler when it's in the jug is a result of this refraction, and our eyeballs actually use this property of light refraction in order to work. So you've probably heard before the fact that your eyeballs actually see everything upside down, and then your brain has to correct it to flip your image right side up again. And the scientific reason why your eyeballs see the world upside down is because of refraction. So, I'm not a very good artist, but here is my diagram of the way your eyeball refracts light. So we're going to talk about two parts of the eyeball here, the lens and the retina. The lens is really the very outside portion of your eye. It's really the glassy surface of your eyeball. You can compare the glassy surface of your eyeball to the sloped surface of a magnifying glass or something like that. They work in exactly the same way. Your retina is the hole in the very center of your eyeball. That is the part of your eye that collects light and forms the image that you see. So, here in my diagram, we have a person that you're looking at. Here's the person over here. And the way that our eyeballs actually see things, when you look across the room and you see another person, you're actually just seeing the light that's bouncing off of that person. So all of these lines here represent the light that's bouncing off of that person. Now, in our previous classes, we've talked about the fact that white light that comes out of light bulbs or comes out of the sun is made up of all of the different wavelengths of the rainbow. That's what our colors are. So that's why we get rainbows. When we split those beams of white light, we can see red, orange, yellow, all the colors of the rainbow. So that's what we have here. All of those, that full spectrum that we call it, of light is bouncing off of this person, and all of that light will pass through your lens, the surface of your eye. The lens acts just like a magnifying glass, as we said, and it bends all of this light. That's refraction. The light is moving through the air, and it hits the lens of your eyeball, and as it moves through that lens, it has to move a little bit slower, and so the light's angle changes, and also the shape of your eyeball lens is specially made to bend all of that light, to bend all of the light towards one spot, towards your retina. So that's what you're seeing here. The light that's bouncing off the person that you're looking at is hitting your eyeball lens, and it's all being focused down into the retina. Now, when that light bends into the retina, those beams of light are actually basically going to continue through your retina, and you can see that here is the red spectrum of light that's coming up here. But when it bends through the lens and through the retina, now the red spectrum of light is all the way down here at the bottom. The violet spectrum, which is the last spectrum, was at the bottom here, but since we bent it through the lens and through the retina, now it's at the top here. We have basically flipped the whole light spectrum upside down as we refract it through the retina of your eyeball. And that's why your eyes interpret the world as being upside down, because of how the lens works. Your brain does a really good job of then flipping that image back right side up so that it makes sense to you. So, we're going to do two quick demonstrations here to really show you exactly how this refraction is working. So to demonstrate how the lens and retina of your eyeball works, in this little demonstration, our jar of water here is going to be the lens, and the back of the paper is going to be the retina, the part of your eye that it's almost like a photograph. It's the part of your eye where the light image is kind of imprinted. So, here's the image that we're going to be looking at. Very simple. A red bar and a blue bar. So, watch. As of right now, the blue bar is on the left side of our vision, and the red bar is on the right side. But watch what happens as I look at it through a lens. Can you see how these two bars have changed places? Now, the red bar is on the left side, and the blue bar is on the right side. The lens has flipped the image. This is exactly what's happening inside of your eyeball, as I just explained. This is how all lenses work. If you take a magnifying glass and you look at just about anything, you can recreate this exact demonstration at your home. Zoom kind of in and out using the magnifying glass over any image, and eventually you'll be able to see it flip. And that's the job that the lens is doing. Our second demonstration is going to hopefully show more clearly how a lens can bend light, and then how the image that light produces gets flipped because of the bend that the lens creates. So in order to show this demonstration, we're going to have to go into a very dark place. What we're going to see is we're going to create two beams of light using really just holes cut in a shoebox. And we're going to again use our same jar of water here to bend those beams of light. So I have cut the two slits in my shoebox here, and I have my flashlight pressed right up against it. So you should be able to pretty clearly see the two separate beams of light that are being created here. There is one coming off to the left and one coming off to the right inside of the shoebox. The reason that they're not perfectly straight beams of light is that if you look at most any flashlight, the bulb of any flashlight, there's a cone around the bulb that actually causes the light to come out in the shape of a cone. So that's why our light, even though it's going through the slits here, it's going off at an angle. So, again, here is my water lens. I'm going to place the lens right in the way of the beams. So, hopefully you can see how those beams are now being bent and refracted. The two beams that are coming out of here are going through the water. The water is bending them. As a result, they're coming out here and they're actually crossing over one another before they hit the back there. There, that's very good. So, it's a little hard to see where they're crossing. That might help you. So this image at the end here is reversed. The bottom beam here is the top beam here, and the top beam at the beginning is the bottom beam at the end. When I remove the jar, then the beams are right side up again, basically. When I put the jar in the way, the beams cross. You should be able to see an X right along here where those beams are crossing one another. I hope those two demonstrations helped you to see a little bit more clearly how lenses work. So we humans use lenses quite often in our everyday lives. Think of, again, like we talked about, something like a magnifying glass or even something large like a lighthouse. Humans didn't really invent lenses. Lenses are a kind of structure that are borrowed from nature, right? Most eyeballs of mammals and birds and lots of higher animals are pretty much the same kind of lens that humans build today to focus light. So the lens is a very cool, I don't know if you could call it a machine, but it's a cool object that is used to take advantage of refraction, this property that light has to be able to bend through other material. So you at home can try out either of the demonstrations that we did today, and I also encourage you to play around with light and refraction to see for yourself how it works. As spring is coming on here and the weather is getting warmer, I encourage you to get outside, play around near the water, in the water, and in ponds and lakes you'll really be able to see how refraction is working. You've probably already noticed just in your lifetime how objects in a pond are never actually where they seem to be. That is because of refraction. Whenever you see an object in a pond or a lake, because of the way that the light bends through the water, it's going to seem to be in a different place from where it actually is. So hopefully all that we did today has helped you to understand a little bit better exactly how light and refraction works. Thank you very much for watching the Fairbanks Museum Earth Science Lab today.